YouTube channel. You can just never stop once you make one.
Really? See, I just kind of forget. I don't really think about it very much. But I'm old, and I'm not like hip like you guys. I'm not.
Do you have a YouTube channel? No, I don't.
Hey, I have a question. I'm going to start some stuff up here today. I don't know if you guys noticed up here when we started this, but we had a deck of cards up here that I wanted to look at. Oh, where was it? Here they are, right there, deck of cards, okay? So, yeah, we might. I might play a little bit of cards in here, okay? So, I always sometimes make the mistake of saying, oh, it's a deck of cards, and assume that everybody knows what's in a deck of cards, but
yeah, that question online.
Yeah.
sometimes I'm like, maybe I need to talk to the kids about this here first in terms of what a deck of cards looks like. So well, first of all, let's talk. How many suits here?
4.
Okay, what's the first suit?
Diamond, spade, clubs.
I thought suits were the face cards.
Okay, what's that? You thought what was a face card? Okay, so I better, again, this is me, and I got to thinking about this the other day. I was like, I probably should have put that up the other day, but we might need this today. What are my face cards?
Jacks, queens, and kings.
Okay, there's a face to them, right? Okay. So how many total face cards are there?
You got 12 right there, another 3 there, that's 6, another 2 there's 4.
So there's going to be 12 face cards, 4 suits, right? How many total cards?
52.
Okay, there's 52. So let's just make sure we all agree. There's 52 total cards, right? There's 4 different suits. And how many different face cards? 12. Okay, so we're going to come back to this and refer to it, but I want to make sure we're okay with this, okay? Guys, I pick a card at random. What's the probability it's a jack? 4 out of 52. What's the probability I get a face card? 12 out of 52. Now, listen to this one. Okay. What's the probability I get a club or a jack?
So I played that game, that doesn't work.
What if I get a club or a jack? What's the probability of getting a club or a jack?
With the face?
How many cards are clubs, kids?
That's a king, and then you can board kings.
13, right?
What color?
Okay, listen to the question. What's the probability I get either, if I draw a card, what's the probability it's either clubs or a jack?
You got like 1 out of 52.
26 out of
Well, how many are clubs, kids?
50%.
50. No.
13, and then this would be a jack, right? This would be a jack, but haven't I already accounted for that in
13.
clubs?
Yes, sir.
That's a jack, and that's a jack. So how many cards would win for us if it's either clubs or a jack? So 16 out of what?
52.
Now listen to this question. What's the probability that I draw a card that's clubs and a jack? 1 out of 52. Is there a difference between and or when we're talking about probabilities?
Because one includes both. One
Exactly. Okay, one includes, you can either get a club or a jack and win, but the other one's saying the card has to be clubs and it also has to be what? Okay, so there's going to be a big difference. And that's kind of what we're going to talk about today in our notes. We're going to start talking about probability of what's known as disjoint and overlapping events. Okay? So those words and or are going to have a lot to do with what it is that we're going to talk about today. Okay? So 5.4 titled Probability of what's known as disjoint and overlapping events. We'll look at this here in a little bit in terms of vocab, but the essential question for me. How about a volunteer to read my essential question?
I got you.
Thanks, Michael.
How can you find probabilities of disjoint and overlapping events?
Okay, disjoint and overlapping events. Okay, I'll go back to my cards. Go back to my cards. When I said what's the probability of finding a club or a jack, what event overlaps? Jack of what? Jack of clubs is an overlapping event. It could either be the jack that it's satisfied, or it could be the clubs part that it's satisfied. So we're going to talk about what happens to probabilities when we talk about finding the probability of this or this happening, and actually both are happening at the same time. What's that probability look like? So those are going to be some overlapping events that we'll talk about. Now we're also going to talk about things that are disjoint, things that can't happen at the same time. So in order to answer that question, we need to be able to find probabilities of compound events, compound meaning more than one, okay? And now we're going to use more than one probability rule to solve real life problems. Okay? So let's talk right here. A compound event. Somebody want to volunteer to read compound event for me? Thanks, Jacob.
The union or intersection of two events is called a compound event.
The union or intersection of two events is called a compound event. Okay? If you see the word or is like a union. If you see the word and is like an intersection. And we'll talk about those here in a little bit. Okay? How about overlapping events? Volunteer to read overlapping events for me. Go ahead, Michael.
Two events are overlapping when they have one or more outcomes in common, as shown in the first two diagrams.
Okay, so we'll look at some diagrams here at the bottom. We'll see what that looks like here. But yeah, overlapping events are going to be two events when they have one or more outcomes in common. All right? I'll get you the drawing down below there here in a second and show you what this looks like. Just going to write C below here in a second, okay? How about disjoint or mutually exclusive events? How about a volunteer to read that? Go ahead, Audrey.
Two events are disjoint or mutually exclusive when they have no outcomes in common, as shown in the third diagram.
Okay, so we're going to write down here C below as well. Okay? So let's talk about what's going on here. What are we really talking about? Guys, in order to see what these things mean in terms of their definition, to visually see what they mean in terms of their definition, we use what's known as a Venn diagram. You guys have talked about Venn diagrams before. What are Venn diagrams?
I'm not very
Two circles with the things in common.
I'm not very good at the.
We'll get it. So Venn diagrams are going to kind of be diagrams that you might have event A and event B. Sometimes event A and event B do what?
They overlap.
They overlap. Okay. So the compound events that I want to talk about right here. So you've seen Venn diagrams before. The events that I want to show you right here quickly are the following. Okay. We're going to talk about the union. Of event A and B down here. We'll talk about the intersection. Intersection of A and B in the second part there. And then that third point, the intersection of A and B is empty. That says intersection, okay? I don't like that. Okay, so here's the deal. Let's say I have some events. I don't like that either. You're going to draw two circles. I'm going to do my best to draw two circles here. Here's one. Here's another.
Do they have to be overlapping?
I want these to be overlapping, like so, yes.
That's what a Venn diagram is. Yeah, you did.
Now, children.
Okay.
Can't we all just get along?
We've had a good run.
Sounds like it. Okay, union of A and B. All right, I don't know what these are, but here's the deal, kids. Within A and B, I'm going to call the circle on the left event A, event B. And here's the situation, kids. There might be a lot of different points in A. And there might be a lot of different points in B, but there also might be a lot of points in what? Both of them. Okay, so when we talk about the union of A and B, it's like your events A and your events B all brought together. This is kind of like saying, well, in this situation, what we would like to do is have all events A and all events B, they're all together. Okay? These are all together, and I should do it kind of like this. Hopefully this works. I don't know if it will or not. We'll see. Hopefully it works. Ah, it did. That's awesome. Okay, when I overlap this, we're saying we're including everything. Okay? A union of A and B is all the points in B and all the points in A all put together. It's every single one of them. Okay? I can either get something from A or I can get something from B. Sometimes it'll be in what? Well, both. Okay? Now, the intersection of A and B. How do you think the union, if the union is everything in A and everything in B, this is like saying, well,
I bet it's the middle.
this is like the or part. I can have something from A or something from B. Okay? And this is going to be a situation where we have the word and right here. Okay, what did you say it was going to be there? What did you think it was going to be there, Adam?
The middle piece.
I think it's going to be the middle piece. Okay, so you're saying right here, if I take right here, where are my points that are both in A and B? So if I say, hey, here's A, and here is B, I might say, well, the points that are in A and B, I might have a bunch of points A, and I might have a bunch of points B, but the points that are in both A and B are where now? Well, they're right there. So what we're really talking about, or what we're really focusing on, is this part right there. We really want to focus on that part right there. So that intersection and is going to be the part right in the middle. It's the points that are both in A and also in what? B. Okay? Kind of if I go back to the cards, if I say what's the probability of getting a jack or a club, it would be all the clubs plus the other 3 jacks, right? Any of those would work. But I'm talking about the card has to be a jack and a club. How many cards are you talking about then? Well, just one, because you have to satisfy both conditions. You have to be an A and B, okay? These are considered events. These are considered events that would be, what's the word? They overlap with each other, okay? This one here is a diagram of something that's going to overlap. Whoops, didn't want to do that. This is going to be something that overlaps and overlaps. Okay, now events that what we consider disjoint or mutually exclusive. 2 events are disjoint or mutually exclusive when they have no common outcomes. So as an example, this is what a Venn diagram would look like for this. Event A would be over here. Event B would be over here. What do they share? What points do they share?
Nothing.
Nothing.
Because they're not even connected.
Okay, so we would say that this is, the word disjoint simply means what, kids? You're going to hear that term or that phrase mutually exclusive thrown around a lot in this section. It just means that they don't happen, okay? So this here would be a mutually, I spelled that wrong. This is mutually exclusive or disjoint, if you will. Nothing shared. It's kind of like saying this. What's the probability today that if I pick a student from Union High School, if I pick a random student from Union High School, what's the probability they're going to school at Dyke first?
0.
Not happening because the Union.
100%. They go to Union.
Okay.
Only
Makes
dogs
sense?
go to Daddy.
Right?
Wow, aren't you this smart?
All right. Good on terms, first of all. You understand what an overlapping event is? You can either have the union of an overlapping event or the what? Intersection. Intersection is the part where they meet and the part that's shared. Union is everything in A and everything in B put together. Disjoint means that nothing in common. Okay. So let's roll on to the next page here. Where did I set my pen down at, kids? There it is. Any questions so far?
Wouldn't it be awful if you like connected to someone?
Okay, page 2. This is a really big concept right here. You're going to want to make sure that you highlight this, do what you need to do to highlight this. Okay, that's pretty important stuff up here. What's that? These two formulas are going to be really important for you. This is probability of what, kids? Probability of compound events. So here we go. If A and B are any two events, then the probability of A or B is what? Probability of A or B is equal to probability of what? Plus, minus the probability of A and B at the same time. Okay?
I don't like when I write that.
I don't either. Okay? But what it's really saying is this. Let's put this in terms of the picture. I'm going to go back a previous page. What this is really saying is this. If I look at this diagram down here, the probability of A would be this first circle, wouldn't it? And then the probability of B would be this second circle. Well, really, this whole yellow area, we have to, how many times in this circle and this circle have I accounted for this area right here in the middle now? Twice. So in order to understand what the whole yellow area is, we have to subtract that out one time to make this one complete yellow area. If I just say the probability of A plus the probability of B, this inside area gets accounted for twice. That's why I have to take the probability of A and B out of that once to make sure that that works. So that's going to be a formula there that you're going to want to make sure that you understand when we're talking about compound events. Okay? It says here, if A and B are disjoint events. Disjoint mean what? They don't overlap. So if they're disjoint, like in this picture right here, probability of it happening is just the probability of this plus this. Okay? I don't have to subtract out the middle part because there is absolutely no overlap there. Does that make sense?
Yes, sir.
Okay. How was it, Ty?
Pretty good.
Good. You'll need to get caught up on whatever part we are, but here's where we're at right now. Okay. Let's talk about these two ideas then. Example 1 says finding the probability of what, kids? Disjoint events. So here's the formula for disjoint events. The probability of A or B happening is going to be what? Probability of A plus. Let's just talk. It says 2 6-sided dice are rolled. Okay? What's the probability that the sum of the numbers rolled is a multiple of what? Or is? Okay, these are disjoint because is 5 even a multiple of 4?
No.
Absolutely not. Let's get a table up here. How many die are rolled again? Or how many dice are rolled?
2.
Okay, so what are the outcomes for the first die?
1,
2.
All right, then the second die over here. 1, 2.
6 outcomes.
Yeah, but not ones that.
Okay, so it says what's the probability that the sum is a what?
4.
Multiple of what?
Oh, yeah.
Okay, so let's get our subs in here first. Let me write my sums in here. So this would be 2, wouldn't it?
Yeah.
And you don't need to write this down.
Okay.
But if you want to, it might help. I don't know. It's up to you.
That's a lot of numbers.
Careful. My hand
Yeah,
is starting
it's
to.
Hear someone talking about it. I don't know who it is.
You.
Okay.
Something's wrong with all these kids.
Yeah. Hold it.
All right, kids, up here what we're going to do is this. It says, what's the probability if I roll 2 dice that, first of all, it's a multiple of what?
4.
So my multiples of 4 up there is no sums. Would be 4, 8, and what?
12.
So anywhere where we would get a 4, an 8, What's the last multiple of 4 in this table? Okay, so the probability that we get a multiple of 4.
Wow.
Careful.
But it only does it if you.
There's so many 8s on there.
What's that?
It only circle if you do it like close to a circle.
Kind of, yeah.
Mess it up.
I was at the end. It starts zigzagging its way on the end there. How many are multiples of 4 up there, kids? 1, 2, 3, 4, 5, 6, 7, 8, 9. Are any of those multiples of 4 a sum of 5?
No.
So is there any overlapping going on here?
No.
So this would be what type of events when I compare A and B? These would be what type of events? Disjoint, okay? How many are multiples of 4 again? 9 out of how many totals down here?
36.
So I'm going to say this right now. So the probability of this, since these are, since these are disjoint events, the probability for multiple of 4 is 9 out of 36, you said? Plus then, or we get a 5, probability of a 5. Well, we better go back to see how many sums were 5. How many sums are 5 here, kids?
4.
1, 2, 3, 4. Did anything in blue overlap anything in yellow? No. So what's the probability we get a multiple of 4 or a 5? How many 5s were there again?
4.
Okay, so I'll go back to my notes. So this would be
4 out of 36.
plus 4 out of 36.
Oh, it's the other.
Yep, so here's the deal. Probability of disjoint events. Probability of A happening, multiple of 4, or B is the probability of A plus what? See, so what's 9 over 36 plus 4 over 36 equal?
13 over 36.
Okay, so let's turn that to a percent, nearest tenth. Somebody run 13 divided by 36 for me.
Adam, this is new.
No.
I do the reading, you do the math.
Someone can carry the team today.
I was going to say about 36.1%.
See, now you're going to make it.
That's alright. She can.
13 is the prime number. No, it's. Yeah, it is.
36 point. Okay, so I like to go nearest tenth on this. So 36.1%. Thanks, Allie. Okay, so if events are disjoint, it's just the probability of A plus the probability of what? B. Okay, now, I want to talk about the difference here. Finding the probability not of disjoint events, but what's the word here, kids? Overlapping events. If events overlap, then I've got to look at this one right here. Okay, this one here is disjoint events. This top one right here, maybe make a note. This is going to be a formula for events that do what?
Overlap.
Maybe they overlap. Okay.
The first one is?
Yep. So it says a bag contains cards numbered 1 through what?
20.
One card is randomly selected. What is the probability that the number on the card is a multiple of 3 or a multiple of what?
4.
Ooh.
And or.
There you go. Adam, that's the math part. This is where your time comes.
Okay. Let's look at this. How many cards are in there first, kids? 20. Okay, so the probability that this happens, first of all, let's list the multiples of 4 first. Or I'm sorry, multiples of 3 first, up to 20. So this would be 3.
3, 6, 9, 11.
12, right?
Oh my god.
Jacob. Oh my god.
It's Monday, right?
12, 15, 18.
Okay, so hold on a second. We've got 3, 6, 9, 12, 15, and 18. Okay, so how many of these for event A?
Weird.
How many multiples of 3 are there in that set, 1 through 20?
6.
So there's going to be a 6 in 20 chance that I get one of those numbers. Okay, how about your multiples of 4?
4.
8, 12, 16, 20.
So how many are there?
4.
5 out of what?
Do you replace it?
Can we do the ones now?
5 out of 20. But my question, kids, in those two data sets, A and B, A, the multiples of 3, B, the multiples of 4, is there anything that overlaps? Any value that overlaps with itself?
12.
Wow.
Ooh. So how many numbers overlap of the 20?
1. So you have to subtract 1 because you can't count twice.
Exactly.
Yeah, up to 20, right?
Yeah, because the 12 satisfies the idea of multiple of 3 and multiple of 4.
You're right.
It says you only satisfy one of these, so we can't do that. Since these are overlapping events, we have to do the probability of multiple of 3 plus the probability of multiple of 4 minus the probability of multiple of 3 and what else?
That's a long.
Multiple of 3 and multiple of 4, right? So what was the multiple of 3 probability again, kids? 6 out of 20. Yep, my 6 multiples of 3 are 3, 6, 9, 12, 15, and 18. So 6 out of 20 here. Okay? Now, guys, I have to take that out because 12 would have already satisfied this right here. I can't count that down here again because we've already exhausted that idea. So really, the 12 is still here. What was the probability for multiples of 4?
5, but you have to subtract.
5 out of 20.
Gotta subtract 1.
And then minus, this is the overlapping part. What number overlapped in those two lists of numbers?
12.
12. How many numbers overlapped?
1.
Just the one. So it would subtract what here, kids? Minus 112. Okay. Whoops. 1/20th. I'm sorry. Thinking 12. I'm thinking 12 because that was the multiple.
And then that's perfect. 10 out of 20. We can simplify it.
Yep, so this makes that 10 out of 20. So what's the chances that this is going to happen?
50%.
There's a 50% chance that this is going to happen. Okay.
Yeah, we said just gonna, but
Yeah, it hasn't.
it's pretty good.
I wish it snowed.
We should add a turtle in it.
Yeah,
Oh, it wasn't bad.
Yeah, because it might
I
have
saw
snowed.
4 car accidents.
I thought maybe Friday
Yeah, I
morning when it
saw
was
3.
foggy.
We
I
started
thought
sliding around the corner pretty good.
that was rough in the rural areas.
Did you see the person behind you last night? It like turned around.
Okay, so kids,
Is going in a-
probability formula for overlapping events. I'm going to write it down again. Probability of A plus what? Probability of B minus the probability of what and what?
A and B, I'm guessing.
Exactly. Probability of A and B was like the 12's overlapping. 12 happened up top, and it happened right here. Okay? All right, so let's use a formula to find the probability of A and B. This is an interesting problem. All right, kids.
If you want flex tape, let's see.
It says out of 45 customers, kids,
It's not even a thing.
at a breakfast cafe. So how many customers do we have?
45.
42 customers bought either coffee or what?
Juice. Orange juice.
Okay, it says there were 30 customers who did what? And there were 40 customers who bought what? What is the probability that a randomly selected customer bought both coffee and what?
Wait, this isn't adding up.
Okay.
No one likes to buy coffee and orange juice.
I do.
You do.
But I'm a tomato juice and coffee guy when I go out for breakfast. Who said that? It's good.
Tomato. I don't like tomatoes.
Keeps my hair on top of my head. Did you know that?
Tomato juice is fine.
Tomato juice keeps you from going bald.
No, it doesn't. Stop lying.
Stop making that up.
Yes, you are.
Yes, you are.
How do you know?
Because I've tried it before.
Yeah, I used to drink like that.
You're not going
Orange
bald.
stuff.
Yeah.
Orange. No, it's just tomato juice. It's good. It's like drinking.
All right, let's talk here, kids. Let's let event A be the event that the person's drinking what first? What did they list here first? There were,
Oh, orange juice.
let's do orange juice, okay? Let's let event B be
Coffee.
coffee breath.
Coffee.
Why do you breathe on me with coffee breath?
I would like drink a lot of coffee.
I'm gonna watch this.
Probability of A and B then, kids, is OJ and what together?
O.J. Simpson.
Oh. It's funny because he's in
All right, kids, let's talk. It says there's how many customers totally? Of which 30 have orange juice and 40 have what? Okay, it says what's the probability that a randomly selected customer bought both coffee and orange juice. Okay? All right, this is a tough one. This is a tough one. This is a tough one. I'm going to go back to my notes up top here. Is that okay? Is it possible that somebody could have coffee and orange juice together?
It's gonna have to be.
Okay?
But that's weird. They're hot and cold.
So we got to find this part right here, right? Right here, right?
Yeah, I didn't specify if it's cold.
Are we good with that?
Yes.
Okay, listen to what we say here. So I'm going to go back to this right here. It says, of the 45 people, right off the bat, 42
I know how to do
bought either what?
Coffee or
So isn't this like my A or B part right here? Okay, so the probability of A or B, and I'm going to write this whole formula down. The probability of A or B is equal to the probability of A plus what, kids? Minus what? Probability of A and B. Okay, so let's talk right here. What is the probability of A or B in this problem right here? 45, it says 42 either have coffee or what?
Orange.
So what could I put in for the probability of P, A, or B right off the bat? 42 out of what?
45.
Has to equal the following, kids. Okay? 42 out of 45 has to equal the following. What's the probability of A? Well, the probability of just A is the number of customers we know for sure have what? Orange juice. How many kids have orange juice? Or how many people have orange juice?
I do. Not me.
30.
30. So probability of A is 30 out of 45. Plus, okay, probability of B, those people that have coffee. How many have coffee?
40.
40 out of 45. That's going to equal, or I'm sorry, then we would subtract out the probability of A and B, so some number here, X over 45. They want to know what's the probability that they have both coffee and orange juice right here. Okay, here's the deal. How about the 30 and the 40 right there? What's that going to add up to?
70.
So we have 42 over 45 equals 70 over 45. How much would I have to subtract from 70 to get back down to 42?
Let's take
28.
28, right? So what's that X value have to be?
28.
So what that's saying is there are 28 people that have
Both.
Oh,
both, right?
Diego.
Okay, so I need to make some room up here quickly. Give me a second, kids. So what's that make the X value here, kids?
28.
So X equal 28, which means 28 out of probability of, I'm going to put A and B here like so, would be 28 out of what? 28 out of 45. What is that as a percent?
It's like 670, maybe.
I think when you divide that out, I want to say it's close to 63 maybe.
62.222.
So about 62%, 62.2% if you want to write that down there. Okay? 62.2%. Okay, so guys, really what we did, we just plugged numbers in for this formula, didn't we? Didn't we know the probability of A or B? Because it said coffee or orange juice right away, 42 of them. Didn't we know the probability of just our orange juice drinkers was 30 out of 45? The probability of just your coffee drinkers was 40 out of 45. We used all that information to say, how many have both? Well, in this case, it turned out to be 28 of the what? 45 had both, okay? All right, that's kind of an upper level problem here. And I thought that that was kind of tough. And then all of a sudden, they say, hey, take a look at this next one.
Another one that's harder?
Yeah, it's difficult. I want to get it started. We're not going to finish it today, but I'd like to get the diagram kind of started here. All right? Anybody need more time with this page? Okay, here we go. I like this problem. It's really interesting, and this is actually true to form. I can remember when my dad was ill, they talked about this right here. I was up at Mayo Clinic a lot with him when he was ill. And I talked to some people up there, like, how do you come up with numbers and stuff like this? And they kind of explained just like this. And I found it fascinating to know that these kind of studies actually go on in a place like that. So I thought, you know, that's really a great way to know that this stuff is important. But it says a medical association estimates that what? 10.9 of the people in the United States have what? A thyroid disorder. Okay, so there's almost 11% of people in the United States have a thyroid disorder. So here's the deal. Suppose that a medical lab has developed a simple diagnostic test that is what?
96%.
96% of the time they are correct.
So it's not
Okay?
accurate.
So here's how this works. It's 96% accurate for people who what?
Have the disorder.
Have the disorder and
99% accurate for the people who do not have the disorder.
okay. So here's the situation. The medical lab gives a test to a randomly selected person. So let's just say I pick one of you kids and say, hey, I'm taking you up there. We're going to see if you have a thyroid disorder or not. Okay? All right. The medical lab gives a test to a randomly selected person. It says, what's the probability that the diagnosis is correct? Okay?
Oh, it's thyroid.
Yeah.
No, that's like up here.
Okay? All right, let's talk. Here's how this is going to set up here. Let's get a diagram. First of all, kids, what percent of people have the diagnosis? Or 10.9%. So I'm going to say right here, the first thing we do is this. I'm going to put a box down here and say, we're talking about the population of the whole what, kids? Okay, so I'm going to write down U.S. population like this, right here. Okay? In the U.S. population, some people have a disorder, some people
Do not.
okay. All right, so I'm going to call event A up here. Event A, person has a thyroid disorder. Okay? That person has a disorder, which means event B is then either person has it or they don't, right? So event B is going to be what? They do not have a disorder. Okay. What was the percent that this person had a disorder? Okay, I'm going to put a decimal up here to it. I'm going to put a 0.109 up here. 10.9% chance that they had a disorder. So what's the chance that they don't then?
89.1. Is that right?
Mm-hmm. So 0.891. Yeah, you would just take 100% minus 10.9%, right? And that's 89.1%. Okay? Are you good with that? Now I'll show you why we're doing this here, but the last thing I'm going to run off of this in this diagram, put two trees right off, or two branches off of event A here, and two branches off of event B. Okay?
So it's accurate, isn't it?
You're a tree
Correct.
holder. Shut up.
I love trees. It just gave me this wonderful paper.
Oh yeah, when's the tree day?
So, what about trees?
Arbor Day.
Arbor Day, yeah.
When's
Well,
that?
we're talking about the Untitled tree hugger.
Yeah.
Right. Trees have feelings. What's wrong
Yeah,
with that?
so everyone needs a little love in their life. I'm just giving this.
All right. Here's the deal, kids. It says a medical lab has developed a simple diagnostic test that is 90% accurate for people who what? Have the disorder. So if they have the disorder, the test is either correct or the test is incorrect. Okay? If the test is correct, kids, what percent, if you have the disorder, what percent is the chance that it's correct? 96%. So what's the chance it would be incorrect then? 4%, meaning they had it and it showed up negative. Okay? So I do the same thing down here. What if they don't have a disorder? Well, it says 99 accurate for people who what? Do not have it. So the test is either correct or it is incorrect. So people that do not have it, the test is correct what percent of the time? 0.99, and then it would be incorrect how much? 0.01. And we're going to use these numbers tomorrow to pick up on this, okay? So make sure you have the diagram. I'll finish this up first thing. We'll have some time to do some things in class tomorrow. You guys have a nice day.